Welcome to Team 21008. Our poster is a collection of important information from the overall project. The problem presented to us by the Wheaton College of Optical Sciences Polarization Lab tasked the team with designing a payload enclosure for the environmental and mechanical protection of the infrared channel spectropolarimeter IRCSP, as well as writing software for the data management and telemetry subsystems to be deployed on a 12 to 14-hour NASA high-altitude balloon flight tentatively scheduled for August 14, 2021. Following are the functional requirements that define the scope of our project. These guided the following states of the concept of operations. At pre-launch, the Environmental Control System, ESC, is initialized and activated on takeoff. During the flight, the Environmental Control System will be cooling and maintaining the temperature of the IRCSP while it collects data. This verification was done in the environmental testing chamber shown here. The telemetry subsystem will gather data from the balloon, which will be used to trigger different actions on other subsystems. For example, once the telemetry subsystem detects altitude change, the ESC will turn on. The following test was done by moving our single-board computer upward and verifying that the code was initialized, changing pre-flight state to takeoff. Also, the data management software will be collecting and storing the IRCSP data for post-flight processing as requested by our sponsor.
Top-level system requirements were developed after this analysis of the ConOps, which then helped us to make our system block diagram with all the included subsystems interacting with each other, including the balloon and provided battery power use cases. The environmental control subsystem, which had long lead hardware, was prioritized in the Agile method as our MVP1, with the telemetry and data management subsystems prioritized next. Our third MVP includes a motor design selection that we are not required to build or test. Our hardware design process began with modeling and analysis, including a breakdown of the power that can be provided to each subsystem, a thermal model to show the predicted ambient and internal temperatures during the flight, and a timeline to predict how fast our enclosure will cool in these conditions. This timeline was altered alongside each hardware iteration and showed the increased efficiency of thermal transfer after each version. Several trade studies were conducted during this process, including ones for the active cooling technique, insulation material, and enclosure material. The results of this research concluded that thermoelectric coolers, polystyrene and mylar, and aluminum were the most logical conclusions to these respective questions. The design of the mechanical enclosure went through several iterations shown here. The goals of the following changes between iterations were to reduce machining costs and maximize performance at lower temperatures. Here are a couple SolidWorks hardware drawings for the final design.
For the telemetry subsystem, we performed a trade study for the embedded system. We decided on a TS7800 V2 single-board computer due to its high processing power and low power consumption. The telemetry system flowchart describes the inputs and outputs of the system and what code handles each input and output. The electrical unit schematic describes the physical pinning of the electrical unit, the voltage levels of the wiring.
The data management software design went through a similar process, starting with a performance and delivery schedule-based trade study. The analysis concluded with the post-flight processing scenario being the overall best in performance. A block diagram and flowchart was developed to describe the subsystem functionality and logic implementation of the code. The SRVM outlines the software expectations and requirements requested by the sponsor, which covers storage, file format, creation frequency, and data parsing specific GPS message types.
Based on our torque and vibration studies, we select NMEA 23 motors and the appropriate shock absorber. Here are our sub-assemblies of the two motors used with the bill of materials. And here we can see how our upper motor will keep the instrument in the direction of the flight, and our lower motor will guarantee a 90 degrees field of view.
The following flowchart shows the overall verification plan. This includes several assembly procedures, a safe-to-connect inspection, and preliminary tests done of the hardware before verifying. We verified the telemetry and data management code at a subsystem level before final integration of all parts in preparation for the 12-hour thermal chamber test. The hardware drawings, subassemblies, software documentation, and test sheets are all included in our IDL.
Here are our final deliverables to the sponsor. We have the IRCSP instrument enclosure on the left, and the electronics enclosure housing the single-board computer and the PID loop temperature controller on the right. We have achieved the temperature difference between the hot side and cold side of our TEC of 29 degrees Celsius. However, the hot side of our TEC rests about 12 degrees above ambient. This is due to the inefficiencies of the standoff used between the hot side of the TEC and the heatsink itself. This can be removed to further the efficiency of our system. Under our current design, we have achieved a focal plane array temperature of 15.3 degrees Celsius, which is about 5 degrees below ambient. We have not yet been able to test our system in the environmental chamber.
We use the Visual Studio Remote Development Suite to deploy C++ files or SSH. These files handle different telemetry components. The accelerometer file uses I2C with the onboard accelerometer to detect acceleration events such as takeoff. The TEC TTL file uses TTL to communicate with the external TEC controller to regulate the IRCSP temperature. The balloon file receives NMEA GPS over RS-232, writes the messages to disk, and calculates the ascent rate. The ADC file uses I2C with the onboard ADC and calculates voltages. The NTC decoder extends ADC and calculates the thermistor's temperatures. The main file implements a finite state machine to control, organize, and partition the automata behavior.
The data management software is designed as a two-part system with the image capture code being utilized in flight, which creates an HDFI file type, stores the timestamp when the file was created using the operating system time clock, and captures images and temperature data from the IRCSP. The GPS NMEA parse code is executed post-flight, which opens the same files created in flight. It retrieves a matching timestamp within the GPS data that was recorded in a text file and appends all the corresponding data to the original. The data management software still has additional testing and verification to be performed. A majority of it has already been verified and documented as shown.
The following shows our configuration management plan with our current revisions. The ISR3 will include the full documentation of the hardware as it was built. We completed an inspection report to show that the hardware was assembled correctly and was safe to interface with the IRCSP. We expect to hand off our two fully tested and verified subsystems, the telemetry and data management codes, as well as the fully assembled hardware system, which will have gone through several tests and inspections. We plan to identify any failures, explain potential improvements to be made, as well as the expected performance of the hardware for the full flight ConOps. A 12-hour test within the testing chamber will be the final step towards full system verification, which is scheduled for the first week in May as approved by the sponsor. After senior design, all out-of-scope components will be integrated into our delivered products in preparation for the flight in mid-August. Through this process, we ran into major setbacks. The most significant was our inability to get quotes from machine shops, resulting in extreme long leads. From this, we learned that fabrication of single-run components require extensive networking, and that we should have pivoted focus from hardware testing to software testing earlier on in response to these delays. We also ran into a setback of a defective single-board computer, so in the future, it would be prudent to spend extra money to buy backups of complicated equipment in anticipation of those kinds of defects to save time. Finally, we should have reduced our scope after the first semester in response to requirement volatility that was the result of the parent project still developing as we were working. For example, our design work and analysis was performed under the assumption of a worst-case scenario flight of 32 hours. Only within the last 2 weeks did we learn the flight would only be 12 hours. A reduced scope would have allowed us to be more flexible in editing our analysis, and there would have been less requirements needing to be altered to reflect this new time.
Our final deliverables will include a fully assembled environmental enclosure, the data management and telemetry code on a USB drive and GitHub, and a single-board computer integrated with the hardware. The following slides show our cost tracking, expenses to date, and the delivery status and bill of the hardware components. Finally, we've included the ECR form that was developed on March 12th to discuss changes in project scope and show that our customer is on board with the delivery plan of our subsystems. In summary, our team used agile methodologies to iteratively engineer our final products, which are a result of our detailed design process, trade studies, modeling, and analysis. Our final integration of all subsystems will be the result of our detailed verification plan and extensive testing. To date, the team has put over 1,000 story points in Smartsheets. Special thanks to our sponsor Kira Shanks and Meredith Kapinski and our mentor Kat Merrill. Thanks for watching.